Good afternoon, everyone. I hope you guys are doing good. My name is Mujib. Uh, I'm a data scientist. I have been working as a data scientist for 2 years at Coding School. Um, I'm a mentor for other companies as well as a part time. And I have overall 6 years of experience, out of which 4 years completely into data. So I have trained more than 1000 plus students in Python, SQL, Power BI, Tableau at times, majorly machine learning, deep learning, and generative AI. So in the today's class, we're gonna discuss something called decision tree, classifier, and regressor. Okay, so we'll discuss what that is, how it works internally in a moment. So just like other supervised machine learning algorithms, as you know, supervised machine learning algorithms are those algorithms that are trained under supervision. As in a simple words, you need to have a target variable to train all these supervised machine learning algorithms. So some of the supervised machine learning algorithms are ever famous eminent algorithm, that is linear regression, used for regression problems, logistic regression, used for classification problems. When we have these algorithms, why do we need to learn an algorithm called decision tree algorithm? That is what we need to understand even before learning the decision tree algorithm. Decision tree algorithm is also a supervised machine learning algorithm, just like linear regression and logistic regression. Although these are two separate algorithms, but decision tree itself is capable of doing a task of what linear regression does. Similarly, decision tree can also do a task of what logistic regression does. But yet again, the question is, why do we need decision tree algorithm when we already have linear regression and logistic regression? So there are two answers for that. The first answer is, these two algorithms are called parametric algorithms. Just like parametric test, hypothesis test in statistics, all the tests that assumes all the tests that have assumptions within them, or they want those assumptions to be met before you apply those tests or the algorithms, that algorithms are called as parametric algorithms. So one of the major assumption of these two algorithms is the data should follow linearity, basically. Okay, what if your data is non-linear? If the data is non-linear, both of these algorithms may fail. They may not perform as good as they perform for linear data. There comes decision tree to rescue. Not only that, decision trees are pretty simple to interpret. Okay, you can literally visualize them after you are done with the training of the algorithm, and easy to understand as well. So besides this, we have many more advantages of decision trees. We'll cover them at the end of this session. But let us understand, how does the decision tree work? So as I said, this decision tree works for both regression problem and classification problem, right? So regression problems are are those cases where your target variable is a numerical value or a continuous data, or a numerical value or a continuous target variable. So when you have a target variable that is numerical or continuous, then you apply regression problems. Examples are if you are trying to predict the house price, or if you are trying to predict the salary of an employee, or if you are trying to predict health insurance amount of a customer, or if you are trying to predict the second hand vehicle prices, etc. All these problems are of regression. Okay, so using regression algorithms you can solve these problems, whereas the classification algorithms are those algorithms. I'm just writing a bit fast so that I can complete this recording within the given time. So classification algorithms tend to classify the classes. Let's say if a patient has heart disease or not heart disease, or if an email is a spam or a ham email, is a transaction fraud or genuine, or does a patient have diabetes or not diabetes. Similarly, did the student pass the examination or did he fail, etc. These are the some use cases of classification algorithm, and these are the use cases of regression algorithm. So decision tree works for both of these problems. It can solve both the problems easily. So in general, if you want to understand decision tree algorithm, it's just a tree, okay, or you can call it as a bunch of nested if else statements. That's how simple it is. Okay, so you're gonna have a tree built in this fashion. Okay, so this first node, these are nodes. Okay, these are nodes. If it is the last node, then this is called as leaf node. If it is a last node, then it is called as a leaf node. Similarly, this is also a leaf node, and this is also a leaf node, and this is a decision node. It's a node from which you further divide the data into multiple branches. This is also a decision node, and this is a root node, which is the first ever node of your tree. So how do we select these nodes? What is the math underlying for this algorithm? That we will discuss. Before that, I'll show you practically how this algorithm works with some example. So let me go to a game called Akinator. Okay, this game is completely based on this machine learning algorithm called decision tree. So when you play this game, you will understand this is how exactly your machine learning model works as well. So before you start the game, let me start it from the beginning. So you have an option called play. I'm gonna play. Now it would ask me select the next game thematic. So I'm gonna assume one character, maybe a movie character or TV show character or a sportsman. So I'm gonna click on this. Now it is going to predict what I have thought in my mind. So let's say I've thought of MS Dhoni, who's a sportsman. So at every step it is going to ask me questions. So when I provide the answers appropriately, it is going to classify that properly. So let us try. So is your character a YouTuber? No, my character is not a YouTuber. Is your character of Indian origins? Yes, he is. Does your character play in IPL? Yes, he is. Is your character married to a Bollywood actress? No. Is your character currently more than 40 years old? Yes. Is your character a god or gods? No. Is your character left wing? No. Does your character like cupcakes? Don't know. Is your character linked with Chennai Super Kings? Yes. Is your character a wicket keeper? Yes. See, it has predicted or classified that person as the MS Dhoni. Okay, this is how at every step decision tree algorithm would ask you question, and based on the answers that it gets from the features within, so that it will classify accordingly. So when you train the model, you are going to give your new data to the model, right? So according to that new data, whatever the training it has gone through, it is going to classify the new data that you feed into it. So how are these nodes selected? Okay, how do we select the first node? So let us see with math. So I have this data, ever famous data that we have, that is based on these features. I need to decide whether we're going to play tennis or not. Okay, simple data, easier to understand. One more thing is, these decision trees are built based on two criteria. Okay, so the entire nodes decided based on two criteria. The first criteria is Gini impurity. The second criteria is entropy. So whichever feature gives me low Gini impurity, that will be my node, root node to begin with. Over here, if you are going ahead with the entropy, so with entropy you need to calculate information gain as well. So information gain is nothing but the decrease in entropy after the split is made. So information gain is what you need to calculate if you are going ahead with the entropy to build the trees. So whichever node gives you highest information gain, that will be your feature. So what is entropy and what is Gini impurity? At a high level, both of them talk about the impurity within a node. Let's say you have a node with yes, 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 no, 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 no. So when you look at this node, you see a lot of impurity here, right? It's not a pure node. But if you look at this particular node, this is a pure node, this is a pure node, right? Both are homogeneous nodes. Okay, so with using entropy and Gini impurity, we try to calculate this. Okay, what is the impurity of each of the nodes? Accordingly, we'll try to divide the data further. So, but why do we have two measures? Why can't we only use entropy? Why we have Gini impurity? See, basically, both of them will help you build a tree, but Gini impurity is easier to demonstrate, as in it will be easier for you to calculate the math behind it, as it does not contain log. So if you look at the Gini impurity formula, it is 1 minus sigma I equal to 1 to n pi. These are the probabilities of each of the classes. So in entropy, you're gonna have a logarithmic in it. Okay, log included in the entropy formula. So for that reason, in this demonstration, I'm gonna show you Gini impurity. And also scikit-learn internally by default uses Gini impurity. Hence, we are preferring Gini impurity as it is easier for me to show you with calculations as well. Okay, so let us go to our data set. Okay, this is my data. First of all, as I said, if you are going ahead with the Gini impurity, you need to pick a root node, right? So to pick the root node, you need to have a Gini impurity value. So whichever feature gives me lower Gini impurity, that is the node, or that is the feature I'm going to consider as a root node. So let me start with outlook. Okay, that's the feature that I'm going to pick first, and yes and no, these are the two classes that I'm picking for the decision, from the decision. So let me pick sunny. The unique classes in this particular variable: sunny, overcast, and rainfall. Okay, so these are the three unique classes that I have in my table. So for sunny, I need to calculate how many yes and how many no corresponding to it. So I'll pick sunny rows 1, 2, 3, 4, 5. These are the sunny rows. Let me color them so that it's easier for us to calculate the no's. 1, 2, 3, 3 no's and 2 s, right? So 2 s and 3 no's. Then I'm going to calculate the overcast values: overcast, 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 and overcast. So let me color them with green color. See, I have all s, 4s with no zeros, so I'm going to write 4s and 0 no's. So I will add the total number of instances also here. So 2 plus 3 is 5 and 4 plus 0 is 4. And for rainfall, let us calculate how many s and how many no's have. 1, 2, 3s and 2 no's. 3s and 2 no's, and total is 5. So when you have a subtable created for this particular feature, let me create a table. My next step is to calculate Gini impurity of outlook table when it is sunny. Okay, that's what I need to calculate. And we know the formula, right? 1 minus this formula, this one. So pi means you're going to have, based on the classes, let's say when I write pi, I'm talking about probability of s and then probability of no. Okay, because I have only two classes, right? That would be my formula. So 1 minus p of s minus p of no. That is what I'm going to calculate now. And there is a square also, I forgot, it has a square. Okay, so this will be a square, and this is also a square. Okay, so 1 minus probability of yes, 2 by 5 whole square, minus probability of no, 3 by 5 whole square. Okay, that's my Gini index when it is sunny for outlook column. Similarly, I'm going to calculate for overcast, and I'm going to calculate for rainfall as well. Okay, so 1 minus 4 by 4 whole square, and anyway this is 0, right? So I'm not going to calculate its probability, so I will get 0. Then for this, 1 minus 3 divided by 5, this 3 divided by 5 whole square, minus this 2 divided by 5 whole square. Okay, that's my Gini indexes for this particular column of each of the classes. But I want overall Gini index of this particular column. Okay, I don't want individual Gini indexes, Gini impurities, sorry, not Gini index, Gini impurities. So how do you calculate the overall Gini impurity of each of them? So you just take the weighted average of all these values. So Gini impurity of outlook equal to weighted average means total number of sunny rows divided by total number of values. Okay, so I have 5 sunny rows and total number of rows that I have are 14. So if you calculate 5 plus 5 is 10, 10 plus 4 is 14 into 0.48. So weighted sum means what is the weight of sunny what is the weight of overcast and what is the weight of rainfall in overall Gini index of that Gini impurity of that particular column. So that's what I'm trying to calculate here. Then I have 4 divided by 14 into 0 plus 5 divided by 14. This 5 divided by 14 into this 0.48. Okay, so I repeat, 5 divided by 14, this total, into 0.48 plus 4 divided by total 14 into 0 plus this 5 divided by 14 into 0.48. That's my Gini impurity. Okay, let me color it because we need to come back to this value at a later stage. So this is the Gini impurity of outlook, right? So I need to calculate the Gini impurity of temperature, Gini impurity of humidity, Gini impurity of wind also. So let me decolor everything. So it looks tougher if you haven't done this before, but when you do it on your own, it is really easy. So in temperature, see, the unique values are temperature, hot, mild and cool. So let us create a same table of that sort. So instead of outlook, I'm going to write temperature, yes, no, and total number of instances. I have hot, then mild and cool. So don't worry, I'm going to calculate the Gini indexes for only 1 or 2 nodes. After that I'll just show you rest of the code, because anyway who is going to evaluate this, I understand you may not have the entire time to do it, because when I evaluate the instructors profiles, I just skim over it. Okay, so within, just by listening to the instructor itself, you will understand whether that person has the potential or not. Okay, so I'll make it easy for you. So hot, mild and cold. So let me calculate those rows. This is hot, this is hot, this is hot, and one more hot is this one. These are the 4 rows that I have. So let me color this as well, pink. So out of 4, 2s and 2 no's. So 2s and 2 no's, total are 4. Now the mild ones, mild, the second mild, third mild, fourth mild and fifth mild and sixth mild. There are 6 milds here, so let us give a different color to them. So out of 6 milds, this is not overcast, is, did we miss one moment? So it should be red itself. We are going by mild. Yeah, so mild. Okay, all are mild selected. 1s, 2s, 3s, 4s and 2 no's, right? 4s and 2 no's. This is 6. Alright, next I'll have to look into the cool part. This cool, 1 2 3 4 cools. Out of 4 cools, 3s and 1 no. 3s and 1 no, in total is 4. Okay, so how is 3s? This is 1s, this is 2s and this is 3s and 1 no, this no. Okay, so instances are 4. So let us again calculate Gini impurity of temperature when it is hot, individual Gini impurities, and then weighted average of all of them. So it again, 1 minus probability of yes out of all the instances 4 whole square, minus probability of no out of all the instances whole square. That's my Gini impurity. Similarly, I'm going to calculate it for mild. So 1 minus 4 by 6 whole square minus 2 by 6 whole square. That's my another Gini impurity. Similarly for cool. Okay, here 1 minus 3 by 4 whole square minus 1 by 4 whole square. Okay, that's my Gini impurity for each of the classes within temperature. So I need to calculate the weighted average of the entire column. So how do I do it? Before I do it, I'll show you this total. This is 14. Okay, so weight of hot, weight of mild, and weight of cool in getting the overall Gini impurity of that column. So 4 divided by 14 into 0.5 plus 6 divided by 14 into 0.44 plus 4 divided by 14 into 0.375. Okay, that's my Gini impurity of temperature. Similarly, I'm going to calculate it for humidity and wind. I know for this demo I don't have to do it, but I feel like it tells how much of the knowledge one possesses. So that for that reason I just wanted to justify that I have enough knowledge. Anyway, so yes, no instances, that high and normal, these are the only two instances that I have. So I'll remove this high and normal. So let me decolor everything here again. Okay, so I'll pick high, 2, 3, 4, 5, 6 and 7. These are the highs. I'll give one color. So out of highs, how many yes and how many no's I have? 1 yes, 2 yes, 3 yes. 3 yes I have 1, 2, 3, 4. 4 no's. 3 yes and 4 no's. So 3 yes and 4 no's. Total are 7. Okay. Similarly for normal, 1s, 2s, 3s, 4s, 5s, 6x, 6s and 1 no. So 6s and 1 no. The total is 7. Okay. So Gini impurity of humidity when it is high. So 1 minus 3 by 7 whole square minus 4 by 7 whole square. Okay, so again Gini impurity when it is normal. So 1 minus 6 by 7 whole square minus 1 by 7, 1 by 7 whole square. Okay, so this is 14 again. Now weighted Gini impurity for the entire column, humidity. So equal to 7 by 14 into this plus 7 by 14, this 7 by 14 into this one. That's my Gini impurity for humidity column. So let me color this again. Okay, similarly I'm gonna do the same thing for wind column. So instead of humidity, wind. So wind has strong and weak. So strong, and this is a weak. Okay, so in strong and weak, let us check how many strong and how many weak I have according to their yes and no's. So this is a strong, 2, 3, 4, 5, 6. Okay, 6 strongs I have. So let me differentiate them with the rest. So did I miss anything? No. So 1, 2, 3 yes and 3 no's. Okay, perfect. So I have 3 yes and 3 no's. So let me write them here. 3 yes and 3 no's, and total are 6. Okay, 6 instances. Similarly for weak, 3 yes, 4 s, 5 s, 6 s, 6 s and 2 no's. So I'll show you again. 6 s, this 1, 2, 3, 4, 5, 6 and 2 no's, 1 and 2. Okay, 2 no's, and total is 8, and this total will remain constant, 14. So Gini impurity of wind when it is strong. Okay, so how do you calculate? 1 minus again probability of yes instances out of all the instances whole square minus probability of no instances out of all the instances of strong wind whole square. Similarly for weak, so 1 minus probability of 6 by 8 whole square, this 6 by 8 whole square minus probability of 2 by 8 whole square, actually probability of yes and no. Okay, 0.375. Then I am going to calculate the Gini impurity of wind column. That can be calculated as the weighted sum 6 by 14 into 0.5 plus 8 by 14 into 0.375, and that's my Gini impurity again for the column. And if you see, we are done with all the independent variables. This is the only one that is left, that is a target variable. So we are not going to calculate Gini impurity for that, as that is our target variable. So if you check all these values and put it at one place, let me take this and write it here. Let me just write 0.34. Okay, I'm just taking first two words, not word, digits. Then I'll copy this 0.44. Then Gini impurity of humidity, I'll get 0.36 from here, and Gini impurity of wind. Okay, so 0.42. So if you see, out of all of them, okay, out of all of them, which one is the smaller? Gini impurity of outlook is smaller, right, compared to other, hence that is our root node. Okay, so I'll take this node and write it over here. So my root node is, to get started, my root node is outlook. So as soon as the root node is defined, you need to write the branches from that node depending on the values that this feature contains. So if I go back to this table, outlook has three values. One is sunny, one is overcast, another one is rainfall. So I need to divide the data based on these branches now. So one is sunny, one is overcast, third one is rainfall. So whenever someone wants to decide whether they want to play tennis or not, first thing they'll look at is the outlook. So if it is sunny, what are the decisions that they're gonna make? What are the features that they're going to consider next? If it is overcast, what are the features that they're gonna next look into next? Then if it is rainfall, what are the things that they're going to look at from the data that we already have? Okay, so let us now continue in creating the different nodes. I'll do it for one more and then we'll stop it. Okay, after that I'll show you directly from a table that I show it to my students, where it has all the calculations done. So I'll pick only the sunny rows because I want to check which variable should come here, which node should be here. Should it be temperature, should it be humidity, or should it be wind? So I need to decide, right? So for that reason, I'll segregate sunny rows, overcast rows, and rainfall rows separately. So let us do that. Sunny, 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 sunny. These are the rows that we're gonna segregate now. Okay, so similarly I'll do it for overcast and wind in a moment, but let us do it for this. So sunny is coming from outlook column, this is from temperature, and this is from humidity, and this is from wind, and this is the decision column. So it again, you're going to again segregate, again calculate the Gini impurity based on these features, for these features, because we are not going to calculate again for outlook, right, because we already decided. So for this I'm going to calculate Gini impurity of temperatures. First of all, I need to create a subtable now. Temperature, yes, no, and instances. So hot, here the calculations are a bit faster because we don't have much data. So when it is hot, 1 2 3 both are no, so 2 no's, 0 yes, total instances are 2. So when it is mild, so mild are 2, and 1 yes and 1 no, 1 yes and 1 no, so total are 2. Then I have cool, so in cool I have only yes, okay, 1 and 0, total is 1. Okay, so this is the small table that I have created. Then I'm going to calculate Gini impurity yet again for each of these, hot, and Gini impurity for mild, Gini impurity for cool. So this is for mild and this is for cool. Okay, so formula is same, 1 minus 0 by 2 is 0 itself, so 2 by 2 is 1, so 2 by 2 whole square, and you're going to get 0. Similarly here 1 minus 1 by 2 whole square minus 1 by 2 whole square. Okay, I got 0.5. Here 1 minus 1 by 1 whole square, so 1 by 1 whole square. Okay, now I need overall Gini impurity, right? So weighted sum, 2 by 5, these are 5, 2 plus 2 plus 4, 4 plus 1 is 5, so 2 by 5 into 0 is 0 plus 2 by 5 into 0.5. Anyway this will be 0, right, so leave it. So that's our Gini impurity of temperature. Similarly we'll do it for humidity now. So by this time you might have gotten a little bit bored, but it's okay. So I'll complete this humidity because these steps are not needed, because if you explain one for one node, the rest of the things will remain intact, but I'll just show it for one more node and then we'll stop it. So high and normal. So for high, if you see, all are no's, so for high all are no's, that means 3 no's, 0 yes, so total are 3. Then for normal all are yes, so 2 and 0, total are 2, and here 5 total. So I need to calculate Gini impurity when it is humidity equal to high. One moment guys, sorry guys, somebody knocked my door, so I had to go. Okay, so Gini impurity when humidity is equal to high, so this is again calculated as 1 minus 0 by 3 is 0, 3 by 3 is 1, so 3 by 3 whole square. So Gini impurity of normal, 1 minus 2 by 2 whole square, and this will be 0. Okay, so I got 0. Similarly so overall Gini impurity of humidity will be 0, right, because I have zeros in both the places. So even if I take the weighted average, I'll be getting 0 only, so my Gini impurity is 0 this time. Here Gini impurity of temperature is 0.2. So let me calculate the Gini impurity of wind now, this one last. After that I'll stop it. I'll directly show you what happens next. So wind, yes, no, total instances, weak and strong, right? So weak and then strong. So when it is weak, 1 2 3, so 3 weeks, 1s 2 nos, 1s 2 nos, and for strong 1s and 1 no. So 1s 2 nos, 1s 2 nos, for strong 1s and 1 no. Okay, this is 2 and this is 3. Let us confirm one more time. 1s 2 nos and 1s and 1 no, correct. Okay, so after this guys, again the same boring stuff. We're going to calculate wind equal to weak and Gini impurity of wind equal to strong. Okay, so 1 minus 1 by 3 whole square minus 2 by 3 whole square. Similarly 1 minus 1 by 2 whole square minus 1 by 2 whole square. And Gini impurity overall for wind is 3 by total 5, right? So 3 by 5 into this value plus 2 by 5. 5 is coming from this total, okay, into 0.5. So that's my Gini impurity for wind. Okay, so if you look at this, Gini impurity of humidity is 0, right? So that will be my next node here. So humidity is the next node. So what are the two classes within the humidity? So let us check that. So in humidity we have high and normal, right? So these are further divided into high and normal. So without any further calculations here, I'll show you the leaf node, how it happens. Although decision tree does the calculations, but I'll show you directly. Let me first separate these rows, humidity high and humidity normal when it is sunny. So I have that data. Where is it? Yeah, this is the data. When it is sunny, humidity I have high and humidity I have low. So if you look at this data itself, it's quite visible that whenever it's sunny and high humidity, they are not playing, and whenever there is sunny, I'll just convert this into red. See, whenever it is sunny and whenever it is humidity is high. So these two conditions, see, sunny and humidity is high. What is the leaf node for us? No. Okay, so that will be our no here. So this is our leaf node, and from here we can't split anymore. So this is our leaf node. Okay, so how about when it is normal? So when it is normal, yes. Okay, both are yes. So that's my leaf node. So how are we interpreting this? So anyone who wants to play tennis, he would look at the outlook first. If it is sunny, he then checks humidity. So if it is high, he is not going to play, and if it is normal, he is going to play. But what if he finds out that the outlook is overcast? What is he going to do next? So which feature is he going to consider? Similarly, which feature is he going to consider for rainfall? So we are done with outlook and humidity, right? We are left with only temperature and wind columns. So let us first pick the outlook rows from here. So 1, this is 2, this is 3, and this is 4. Let me color. So if you see this, guys, wherever there is overcast, we have directly yes. So a person is not going to look at the rest of the features. Whenever he sees it's overcast and it is logical also, right? So we're going to play tennis. So straight away, as soon as you see a weather to be overcast, then you're going to play tennis. So there is direct leaf node here in this condition. But when it is rainfall, what is the next feature that you're going to see out of the leftover features? Are you going to see wind, or are you going to see a temperature? What are we going to see? So when I calculated again Gini index of all these two things, I found out that wind has the lowest Gini impurity. So wind will be my next node. Okay, the steps will remain the same to calculate it. So you will pick the rainfall rows separately, and from there on again you calculate the Gini impurity for humidity, temperature and wind separately. So since I know that, first of all let me pick those rainfall rows 1, 2, 3, 4 and 5. These are the 5 rows that I have. Just like sunny rows that I picked, I am picking the rainfall rows now. Okay, so humidity is already fixed, right? So we have made the node of humidity. So I want to check for the temperature and wind, and this is decision, this is humidity column, and this is outlook. So when it is rainfall, what is the next feature you're going to look? So when we calculated the Gini index again for these three, we found out that wind has the lowest Gini impurity. So I'm going to write wind as the next node. Then when it is wind, I need to next check what are the values that I have in wind. So if you see, wind has strong and weak. Okay, so wind has strong and then weak. So when somebody sees outlook is rainfall and it is windy, is that wind strong or weak? So if it is strong, what is he going to do? If it is weak, what is he going to do? So let us check from the data itself. So whenever wind is strong, he is not going to play. So whenever wind is weak, he is going to play. See, for strong there is no, and for weak we have yes. So for strong we have no, and for weak we have yes. Okay, so this is how a tree is built, okay, internally. Let's say if this is not a classification problem, this is, for now this is a classification problem, right? You're going to decide whether to play or not play. If it was a regression problem where you have target variable as numerical variable, this was a numerical variable, okay. So in that case, if that is a regression problem, you take the average of all the nodes within this particular node. Okay, so you started from this feature, but if you have reached this leaf node, you take the average of this node and that will be your output. If you have reached this leaf node, you take the average of all the values within this. Similarly here, average of all the values, or average of all the values and average of all the values, basically average of all the values in the leaf node in the regression problem. Okay, next is how do you evaluate the performance of the decision tree model. So based on the, if it is a classification problem, you would check accuracy, and you would check if the data is imbalanced. Imbalanced means, let's say you have S class 1000 and no class only 50 in your decision column. So this data is imbalanced, so you cannot rely on accuracy at that time. So you can prefer a precision metric or a recall metric or F1 score metric, okay, or ROC AUC curve. So I can explain you all these things, but this video is going to be longer. So to calculate all these things, we need to first create the confusion matrix. Okay, I'll just give you at a higher level what happens. So you will have predicted values here and you will have actual values here. Okay, these are the model predicted values and these are the actual values. So let me show you with the data itself, so that will be better for you. So assume that these are your actual values and these are your model predicted value. So okay, so I create the confusion matrix wherein you will have pass and fail students, actual pass and fail students, and model predicted pass and fail students. So I'm going to check when my actual value is pass, did my model how many instances my model also predicted as pass. So if you see, one pass, 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 so there are 3 instances, so I have 3. Similarly, when my actual value is pass, how many times my model predicted as fail. Okay, so when my actual value is pass, model predicted fail, my actual value is pass, model predicted fail, so 2 instances, so I wrote 2 here. Similarly, when my actual value is fail, and how many times my model incorrectly classified as pass, so fail, pass, so fail, pass, fail and pass, this is the only instance, so I have 1. Similarly, when my actual value is false, how many times my model correctly classified as false, so false, 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 2 times, hence you have 2. So this value is called as false positive, because in reality it is a false class, but my model predicted as pass, hence it is a false positive. This is called as false negative. Okay, so in reality it is pass, but my model said it is fail. Okay, so this is false negative, and this is true positive, means actual is also pass, predicted is also pass. This is true negative, actual is also fail, model also correctly classified it as fail. So this is called as type 2 error, and this is called as type 1 error. Okay, so our main aim, if we are going with precision and recall, we try to reduce these 2 errors that the model makes. So after creating the confusion matrix, you calculate the accuracy. So accuracy is calculated as, out of all the values, you add all these values, TP plus TN divided by all, TP plus TN plus FN plus FP. So let's say you have 10 I'll write it here, 5 pass students and 5 fail students. Okay, so out of all these 10, how many of them my model correctly classified? So how many of them my model classified as pass and fail as fail? So those values are these. So errors made by the model are these things. So you put all these things in the denominator, TP plus FN plus FP, TP plus FN plus FP and TN. Okay, this is in the denominator. The numerator will be TP plus TN, and whatever you get, that is your accuracy. So as I said, you cannot always rely on accuracy, right? So you have to go with precision and recall also if the data is imbalanced. So precision is nothing but, out of all the positives predicted by your model, these are the positives predicted by the model, right? How many of them were actually correct? So 3 were correct out of 4. Similarly, recall is, out of all the actual passes, how many of them, all the passes predicted by the model were actually pass values. Okay, so out of all these, how many of these are correct? So with the formula you will understand better. Out of all the true positives, all these pass values, how many of them my model correctly classified? So let's say out of 5 my model classified only 3, right? So 3 by 5 will be my value. So I'll remove that, 3 by 5, that's my recall, 0.6. Precision is 0.75. So when do you use precision and when do you use recall? Majorly recall is used in medical field or in the manufacturing field, because let's say you have heart disease, and heart disease patients are 10, so you want all the 10 to be correctly classified as pass by your model. Okay, because that is important. So if you classify it as not heart disease, or not cancer patient, that will be detrimental for the patient's life, right? So to avoid that situation, you would want your model to make all these correct and make less number of errors over here for false negative. Whereas for precision, you want all the false positives to be as minimum as possible. So real time use cases of precision, recall and F1 score. F1 score is just the trade off between precision and recall. When you cannot decide which one to go ahead with, you can go ahead with the F1 score. So F1 score is calculated as two into precision into recall by precision plus recall. That's it. Okay, that's a harmonic mean. Now, so in the real time, see, for email search engines and also for email filtering, you use precision metric, and for recall, as I said, medical diagnosis or product defect detection. And F1 score, it is also used for fraud detection. When you cannot decide whether to go ahead with recall or the precision, then you would go for F1 score. Okay, so based on these metrics, you would decide whether your model is performing really well or not. Okay, so if it is not performing, try applying cross validation technique or hyperparameter tuning. So the problems with decision tree is it overfits. Overfits means if you have a data of this sort, it tries to memorize the entire data rather than understanding the underlying pattern or relationship within the data. It tries to memorize it. So when you give a new data to the model, it performs poorly. Okay, so for that reason, either you do pre-pruning, you cut some of the branches, or you would do the post-pruning. Okay, so to avoid the overfitting. But if you don't want to apply these two techniques, you go for the advanced tree techniques such as random forest or XGBoost or gradient boosting or AdaBoost trees. Okay, so that's the major problem with decision trees. And also, if you have in continuous variables, then it takes a lot of time, and also it does not perform that well compared to other algorithms. Okay, the advantages, as I said, interpretability, second one is as I said, it helps us with feature selection within. Okay, if you see outlook, humidity, wind columns are used, and we did not use temperature, so that means it has feature selected. It used only the subset of features to build a decision tree. Okay, that's one of the major advantages. Yeah, it is used for non-linear data as well. That's what I said at the beginning. Okay, these are the pros, okay, of a decision tree. Did I miss anything else? Yeah, that's about it, guys. Thank you so much.